Good morning, one and all. I am here to present a lecture on nonlinear control system design tools. And let me introduce myself. My name is Mrs.A.Vimala Starbino. I am an assistant professor of E&I department of M. Kumaraswamy College of Engineering, Karur. So now I'm here to present a lecture on nonlinear control system design tools. So here first we should know why we are going for a control system. So generally for any control system there are three needs. First need is to suppress the external influence or to suppress the influence of any external disturbances, and then second one is to ensure the stability. Of any system, and then third one is to optimize the performance of any system. So for these three reasons we are going for control system. So generally there are two types of control system. One is linear control system and non-linear control system. For any control system, before we apply any control logic, we need to design a mathematical modeling, because if you go for mathematical modeling, it saves the time and it saves the cost also. For those purposes we are going for mathematical modeling. So first we need to model any system, then we have to apply that logic for a linear control system. But in linear control system, the problem is, for example, when we do any modeling, we always neglect the problem. For example, if you take a CSTR, this is CSTR in the sense it is continuous stirred tank reactor. So this is the jacket. So here we usually want to measure the temperature. This is the stirrer, we want to measure the temperature. So whenever we model this CSTR, we usually consider that the heat given to the surroundings is nil, but generally it is not nil. So this inaccuracy may cause some problem, but in linear control system, for simplicity purposes, we usually neglect this. So this is the problem in linear control system. So that is the reason we are moving to non-linear control system. And then the reason why we are going for non-linear control system is, in this universe all engineering systems are non-linear in nature, or if you take any nature also or any naturally occurring systems, everywhere it is non-linear in nature. So but we cannot change the non-linearity, but if you change the non-linearity, definitely it will affect the system. So that's the reason, instead of changing the non-linearity, if we impose our concentration on the non-linear controller design, then that is well and good. So that is what we are going to discuss here. So non-linear control system is itself a complex system. So it always gives us a challenge for us or for researchers to design some systematic procedure. So any controller design means it has to be come up with non-linear control system procedure, so that we can address the control objectives and design specifications. So here I'm going to present 5 different non-linear control tools, because with one controller tool we cannot apply for any system. So that's the reason we are going for 5 different non-linear controller tools. They are sliding mode control, so it is abbreviated as SMC. And then second one is Lyapunov redesign, and then third one is backstepping, and then fourth one is passivity based control system or passivity based control, I can say, and then the last one is output state, or I can say output feedback. So these are the 5 different non-linear controller tools which are available in this system. And then because since we cannot apply one tool for all sorts of non-linear system, so that's the reason we are having these kind of control systems. So first one is sliding mode control. Here the logic is we need to design a sliding manifold first. Actually what is sliding manifold is, manifold means what? Manifold means it is a set of points, and then if you join all the locus of the points in a particular plane. So this is, I can call it as manifold. So we need to bring the trajectory, or we need to focus the trajectory. Trajectory means what? That is our output of interest. So that is if you want to control any system, so we can consider that output. So we need to trajectory, or we need to follow the particular output. So we have to bring the trajectory to reach the sliding manifold. And then the important feature of manifold is it is insensitive to disturbances. So that is the reason we are using sliding manifold. So in SMC, the important thing is sliding manifold, which is used to bring the trajectory to reach the particular sliding manifold, and then this area is insensitive to disturbances. And the next one is Lyapunov redesign. We all know that for linear control system, in order to go for stability analysis, we have to use Routh criteria, Routh-Hurwitz criteria, whereas in non-linear control system, the stability issues can be analyzed by Lyapunov. So he is the guy who introduced lots of things in non-linear control system. So we are going to use his function for addressing the non-linear control design problems. So here what's the design is, we need to design a Lyapunov function, we call it as V, and then this Lyapunov function nature is, it consists of some discontinuous control action. Discontinuous control action. With this discontinuous control action, we can achieve the target. So that is given by Lyapunov redesign. And the next one is backstepping. Backstepping is a recursive procedure. Actually, it mingles the Lyapunov function with the existing control system, and then the Lyapunov function is used to break the control design problem into different sequences. And then each sequence we can apply for lower order control system. Usually, lower order control system we have less amount of restrictions. So you can easily control the system. So in this way your backstepping works. So it breaks the control design problems into sequence of small design problems. We can apply those design problems for a lower order subsystem. In this way we can achieve stability, and then we can achieve the robustness. So that is given by backstepping. And then whereas the next one is passivity based control system. So in passivity based control system we are going to introduce one new technique which is called as feedback passivation. So here it is going to convert non-passive systems into passive, because passive system nature is that is whatever problem it occurs or it faces, it will not consider those problems. So whatever non-passive systems we have to control into passive systems. So that is forward passivity based control. And then the last one is output feedback. Generally we have two control theory. One is classical control theory, another one is modern control theory. In classical control theory, we always consider the Laplace transform, that is the initial condition, as 0. Whereas because in classical control theory, we know only the initial state, but after some time, or we cannot trace the time. Whereas in modern control theory, we can understand at each and every state how the system behaves. So in order to understand each and every state, sometimes we may not have some sensors to measure all the variables. There we have to estimate it. So estimate in the sense we are going to observe the system. So that is what I am going to do here. That is, instead of taking state feedback, if you take the output feedback, and then you have to use a high observer gain. So observer means estimator. So if you use observer high gain, then we can easily address the issues. So these are the 5 different non-linear control designs told. Now I am going to explain in detail about sliding mode control, how we are going to achieve the non-linearity, or how we are going to overcome the non-linearity in any system. So first one, that is sliding mode control. It is abbreviated as SMC. Okay, so here first let me tell you uncertainty, because non-linearity means what? It is uncertainty. So uncertainty in the plan. So there are 2 reasons we are having these uncertainties. One is, as I have already said, whenever we design CSTR, we always assume that the heat exit to the surroundings as 0. But generally it is there. So since we are neglecting those parameters, but when you actually come into the system, it introduces some heat. So there we have to solve it. So that is called as modeling inaccuracy. So that modeling inaccuracy is called as uncertainty. So one uncertainty type is modeling inaccuracy. And then one more thing is, whenever we design any system, if a system is having some n number of variables, then it leads to nth order system. But generally we cannot solve nth order differential equation. There we have to convert a higher order system into first order with time delay. Whenever you go for first order with time delay, definitely it neglects or it hides lots of non-linearities. So I can call it as modeling inaccuracy. And then the second reason is, in the plant itself, in the plant model itself, You may have some non-linearity, for example, inertia. So in the plant itself we have some non-linearity. So these are the two reasons we are having non-linearity that I can call it as uncertainty. So now I'm going to discuss, or we are going to see how your sliding mode control address this uncertainties. There are two types of uncertainties. Okay, first one is sliding mode characteristic is it is a simple step. We have only simple steps or simple set of procedure for a sliding mode control, and then second one is it ensures stability. It ensures stability, and then third one is it is insensitive to disturbances or uncertainties. So these are the important characteristics of a sliding mode control system. So now I am going to take one non-linear function, then let me tell you how we are going to apply simple steps, and then how the stability is ensured, and then how it is insensitive to disturbances. So for that, so let me take one simple system, non-linear system x. This is the order means that is an order of this system which is equivalent to f of x plus g of x into u. So here x means it is output of interest, that is whatever you want to control. So that is termed as x. So x is state vector which is our output or of interest, and then this f of x and g of x, they are called as non-linear functions. But generally we don't know the non-linear or the amount of or what is the nature of the non-linearity, but we can guess that what impact it can give to the system. So we can restrict that, and then u is the control law. So this is the general control system. So here what we are going to do is we are going to define this in the state vector form. So which is x dot and then x n power minus 1 whole transpose. Actually this is one such canonical form. Generally in state, as I have already said, in modern control theory we are using state model, and then before you design any control system, first you need to check whether the particular system can be controllable or it can be observable. Observable means whether we can be able to estimate it. So in order to have check this controllability and observability, there are some canonical forms. So this is one such canonical form. So always your output of interest has to be represented in terms of state vector. So this is one state vector. Okay, now what we are going to do is first we need to design, or first we have to say what is your control problem. So what is your control problem? That is, first you have to get your output of interest which is x of t, and then you have to track this output of interest for a particular time. So that particular time I am going to name it as xd. xd means desired time, and then this is your actual interest. So first you are going to get this vector, and then you are going to track this vector for a particular time. So this is my control problem. And then next one is, in order to achieve this control problem, or in order to achieve this track, or this tracking should be achievable, means we need to assume that at initial condition, that is at time t equal to 0, your state of or your output of interest should be equivalent to your desired state at the same initial state. That is, at initial condition both your output of interest and then your desired output of interest both should be same. So this is our initial condition. We can name it as initial condition. So this is our control problem. Next one is, to achieve the control problem, we need to assume that on initial condition, that is, this is our output of interest and then this is our desired state. Initially both the system are equal, both the states are equal. So that is our initial condition. Then next one is, we need to define a time varying surface where this x of 0 and xd of 0 can survive on that. So for that I am going to define one time varying surface, and then which is a scalar function. So it is d by dt plus lambda, and then n is the order of the system into x bar. X bar is x minus xd. Actually from this we can say, instead of this we can have x of xd equal to 0 also. This is also we can prove. So that is why I have shown. So x bar is this one, and then for example if your n is 2, that is second order system, your s of t would be x dot plus lambda into x. So now we are going to say that is if this tracking is to be achievable means, then if you allow that variable which exists in the surface, then we can say that our tracking is very much reduced, or this tracking problem can be reduced, or that is we are going to track output of interest whether it is reaching the desired state. So how we can track that? That is, if you allow that variable to be in the surface means, then automatically it is achieved. And then additionally, if we equate this to a 0, so definitely we can easily achieve this. So this is one condition. So this is called as a sliding function, and then this is also called as sliding surface, and then later I will tell you why it is called as sliding surface. So far what we have done, that is, first we have designed the control problem. Once we have designed the control problem, we can achieve the tracking, and then the tracking is very good in this surface because it is equivalent to 0. And then next one is, and then one of the characteristic of sliding mode controller is it is insensitive disturbances. So now we are going to show that this sliding surface is insensitive to disturbances. So for that let me take this equation 1 by 2 d by dt of s square less than or equal to minus eta s. Actually, s is our s of t, the scalar function which I have defined now, and then eta is a positive constant, then again it is a modulus s. So this equation, that is this s square and minus, shows that because s includes what? S includes x and then xd. So this shows that, or whenever you draw a path for this equation, it takes the form, that is it starts from somewhere, and then based on this s square and minus, it is going to terminate at one line. That line is equivalent to 0. So we are going to call this line as s of t. So that is what it is going to say. So this equation says that this s square and minus says that your output trajectory starts from anywhere, but based on this equation it decreases, the distance decreases, and then it hits the surface, and then it stays on the surface. So whatever problem it faces, it will not mind it, it just follow the trajectory, it hits the surface and then it stays on the surface. Hence I can say your s of t is an invariant set. So one of the important characteristic of sliding mode control is it is insensitive to disturbances. So now if I allow my trajectory, or if I allow my output of interest to reach the sliding surface and stay on the sliding surface means, then definitely it is insensitive because this set itself a invariant set. So hereafter I can define the sliding surface. So any function which satisfies this condition is called as sliding condition. So any function which satisfies this condition, that is sliding condition, is called as sliding surface. So now since here s of t, which s of t is equivalent to x dot plus lambda into x. So this is our s of t. So since this function satisfies this sliding condition, I can call this sliding surface, this s of t, as a sliding surface. So now we have designed the sliding surface. Then next one is we need to design the control law. For example, because this I have taken as a second order system, but second order system means it should have a differentiations, the order of differentiation should be 2, but here the order of differentiation is 1. So in order to have double differentiation, so we need to differentiate again so that you can have control law. So this is another point, that is s of t is important, and then in order to have control law u, we need to differentiate once. So with this, let me tell you how to design a control law. So whatever we have seen, let me give a small gist. That is, number 1, we have designed a control problem. Control problem which is x, and then it has to reach the xd. And then second one is we have defined the condition, that is xd of 0 is equivalent to x of 0. And the next one is, in order to achieve this condition, if this variable is in s of t, it is well and good. And then fourth one is we have introduced a sliding condition. Okay, and then this s of t, if it follows the sliding condition, then s of t is called as sliding surface. Okay, now I am going to draw how it looks, how the trajectory reaches the sliding surface. So as per modern control theory, so it is x and then x dot, this is a state model. So here this is our s of t, and then this is my trajectory which starts from any initial condition, and then based on the sliding condition it moves and then it hits the sliding surface and then it slides, and then here I can assume my desired state. So it starts from here and then based on the path it moves slowly and it just terminates at sliding surface and slides over there, because this set is invariant set. So in this way we can show the diagram, but we need to know how long it takes to reach the sliding surface. So again we need to go for the sliding equation, which is 1 by 2 d by dt s square less than or equal to eta. Okay, and then we simplify this. When you differentiate this, it becomes 2s by 2 and then ds by dt less than or equal to eta s, and then 2 cancel, this s and then this s will get cancelled, will be cancelled, then ds is equivalent to minus eta dt, and then in order to get the sliding surface I need to integrate it. So I am going to integrate this with s equal to s of t reach, I can say like this, that is s of t equal to t reach, because my trajectory has to reach. So s of t equal to t reach, and then the lower limit is s of t equal to 0 or t naught I can say, and then ds less than or equal to minus eta, and then again t equal to t reach and then t equal to 0 dt. And then when you solve this, it becomes s of t equal to t reach minus s of t equal to 0 less than or equal to minus eta t reach, t equal to t reach minus t equal to 0. And then this is 0, we can cancel, and then usually in sliding surface the extreme point is s of t equal to 0. So finally we can have like this, that is minus s of t equal to 0 less than or equal to minus eta t reach. So minus minus will get cancelled. So what is t reach? T reach is equivalent to less than or equal to s of t equal to 0 divided by eta. So my trajectory or this trajectory takes s of t equal to 0 divided by the positive constant, means it hits. So this is the time taken by this. So we have designed the, along with that, along with control problem, and then the sliding condition, the sliding surface, along with the last one is, that is t reach. So what is the time taken for the trajectory to reach the sliding surface? So now I am going to take one problem to see how the sliding mode control works. A simple problem. So let me summarize the control procedure. Control design procedure. So now I am going to summarize the control design procedure. So the first control design procedure is, you have to design a control law and then you have to show that this control law satisfying the sliding condition. So in order to have the sliding control law, we need to design, we have to differentiate s of t for this, and then sliding condition already we know what is that, that is 1 by 2 d by dt s square less than equal to minus eta s. This is the sliding condition. So in order to have the feature, that is it is insensitive disturbances, so we need to add some discontinuous functions to the control law. That is, for example, u equal to, so u cap is my current action which I am getting from the equation, and then I have to add plus or minus, I have to add some discontinuous function. So I can say it is some constant into signum of s. Signum. So signum of S is a discontinuous function. So but generally the signum function is very hard to experience in practice, because discontinuous means it is up and down, or you have lots of wear and tear. So generally it has to be addressed. I can show you in the diagram, that is, so this is your sliding surface S of t. So this is my trajectory which hits the surface, and then because of the discontinuous control action, it slides like this, then it reaches xt. Okay, then this is called as chattering. So this chattering has to be avoided, because for this chattering we need high control activity to address this issue. So the next law is, that is, first you need to design a control law, and then the control law has to satisfy the sliding condition. The next one is, in order to experience the insensitive to disturbances, we have to add one discontinuous function. But whenever you add discontinuous function, in practice it is very hard to achieve, because wear and tear would be there, or this is the curve we get it. So this is called as chattering problem. This chattering has to be avoided, because of this chattering we need to apply high control activity, or this chattering may induce or may interfere unwanted high frequency dynamics. So it has to be addressed. So the next one is, you need to smooth the control law, because this control law gives chattering. In order to avoid chattering, you have to smoothen this control law. And then this trajectory, it moves, and then it hits the surface and stays there, and then usually the time constant for this is n minus 1 by lambda, and then lambda is the slope of this sliding surface, n is the order of the system. So this is my design procedure. Now I will show you with one example. So let me take one non-linear system, which is x dot equal to f plus u. So again, this f is a non-linear function. I don't know what kind of non-linear is this, but I can define that this f cap is, that is estimation, that is, this non-linearity should be like this, that I can guess, and then this is my original function. So this difference, if it is less than or equal to f, means then my system is okay. So this is the problem. For this I have given the condition, that is, f cap means my estimation on this non-linearity, and then this is my original non-linearity. If the difference between these two is less than or equal to f is my known function. So this is the condition given. So with this, how to do the control design procedure? First one is, we have to do this s of t, which I have already shown that for a second order system it should be x bar cap plus lambda into x bar. Okay, and then I already told you, that is, in order to have a control law, we have to differentiate this. So s dot of t is equivalent to x bar double dot plus lambda x bar dot, and then this x bar double dot is equivalent to x dot minus xd dot plus lambda into x bar dot, and then this x bar is, we already know it is f plus u. So f plus u minus xd dot plus lambda x dot. So this is my s dot of t, and then now I am going to design the control law. So since I am going to design the control law, I am going to take this as u cap, and then this I could equate this to 0. So now my u cap is equivalent to minus, if this is u cap means f is my estimation. So u cap equal to minus f cap plus xd double dot minus lambda. Okay, so now my control law is ready. And then in order to have this insensitivity, so we have to design a control law as u equal to u cap minus some signum function. So I can put like this signum function. Yes. So the signum function nature is it is equivalent to plus 1 when s is greater than 0. It is equivalent to minus 1 when s is less than 0. So this is my control law. So I am going to consider that, I am going to check whether my control law satisfy the sliding condition. The sliding condition is 1 by 2 d by dt s square less than or equal to minus eta s. So I am going to simplify this. Then when you simplify, it becomes 2s by 2 and then s dot, which is equivalent to 2 cancelled. I can have s as it is. In the place of s dot, I can substitute this value, which is f plus u minus xd double dot plus lambda x bar dot, and then s equal to, in the place of u I can substitute this value, which is u cap minus k signum of, signum I can put as sgn of s, and then minus xd double dot plus lambda, and then again for u cap I can substitute this value f plus, my u cap is minus f cap and then plus xd double dot minus lambda x bar, and then I have to continue this minus k signum of s minus xd double dot plus lambda x bar dot. So we will cancel the terms, this one get cancelled, this one and this one get cancelled. This signum function I can name it as 1 because s is greater than 0. So the remaining terms are so the left hand side, so it is equivalent to s into f minus f cap and then minus k. Next, for f minus f cap I can use this. So since I am going to substitute this equation will become less than or equal to, this is capital F, fs minus ks. Next, if I define k equal to, f plus eta, so it becomes minus fs minus eta s. So ff will get cancelled and then this is equivalent to eta s. So my sliding condition, the sliding condition is left hand side is equivalent to this one. So my sliding condition is achieved. So in this way you have to do this, that is for any control system, for any given problem, first you need to identify the control law, and then once you find the control law you have to check whether it is satisfying the sliding condition. Once the system satisfies the sliding condition, then you can proceed with any simulation like MATLAB tools. Once it is done, then you can implement with the real system. So this is how we can design any sliding mode control. Okay, thank you so much. Okay.